So in this video we are going to discuss the question Thermal and Statistical Physics which appeared in JRF Physical Science examination that occurred in June 2013. So let's continue with first question. The statement is 10 gram of ice at 0 degree Celsius is added to a beaker which contain 30 gram of water at 25 degrees Celsius. Okay, so let's take a look at the problem and try to understand it. Okay, so we are having a water beaker containing 30 gram of water. Okay, and it is at certain temperature. Let's write the parameters which are given to us. The mass of water mw, that is given to us as 30 gram. Okay, and then its temperature is tw, that is equal to 25 degrees Celsius. Okay, and what is the final temperature of the system when it comes to thermal equilibrium? Okay, so we are given the specific heat of water as well as the latent heat of melting of ice. So what is given is, so in this water 10 gram of ice. Okay, so let me write the mass of ice, that is given to be 10 gram, and the T ice, it's 0 degrees Celsius. Okay, and also the latent heat of fusion, so that is given to be, or the melting of ice, that is given to be 80 calorie per gram. And for water the specific heat is given to us. So specific heat, that's the heat divided by the mass, the heat capacity divided by the mass basically. So that is equal to 1 calorie per gram per degree Celsius. Okay, so okay, so when the piece of ice whose mass is 10 grams, so when it is put inside the water, okay, so depending upon the heat exchange between the ice and water, okay, so and depending upon how much energy is available inside the water which is at 25 degrees Celsius, if that energy is sufficient and met the energy requirement to melt 10 gram piece of ice, so only then the complete process will take place. The complete process means only then the ice will melt when the energy which is required to melt this 10 gram piece of ice, that is available in 30 gram of water at 25 degrees Celsius. And if it's not, then the temperature of the water will not change. Okay, so let's take a look at the calculations here. So the heat required to melt 10 gram of ice. Okay, so this is equal to, this is the product of the mass of ice and multiply by the latent heat of fusion, you can say, or the latent heat of melting. Okay, so and mass of ice is 10 gram and latent heat of fusion, it's given to be 80 calorie per gram, and this is equal to 800 calories. So that means in order to melt the ice from ice form into the liquid form at 0 degree Celsius, we require this much amount of energy. Now let's check whether this much amount of energy is available with 30 gram of water at 25 degrees Celsius or not. Okay, so the heat available with 30 gram of water, so this is equal to mass of the water and then multiply by the specific heat of the water, which I call as S, and correspondingly the temperature of the water. Okay, so mass of the water is 30 gram and the specific heat is given to us, it is per degree Celsius, so we need not to convert the temperature in into Kelvin. Okay, so this is 1 calorie per gram per degree Celsius. Okay, so therefore we can multiply with the temperature in Celsius, which is 25 degrees Celsius, so multiply by 25. Okay, so this is equal to 750 calories. Okay, so the available energy is 750 calories, and the energy which is required, that is 800 calories. So that means the point is that the ice will not melt completely. Okay, so there is an offset of 50 calories, so there will be a certain amount of ice will remain as it is. Okay, so therefore the final temperature, or what you can say, ice will not melt completely. So this implies that the temperature of the system mean a ice water system. So a certain amount of ice that may melt, because it's in the requirement is of that of 800 calorie, whereas the available energy is 750 calories. Therefore T system will be at 0 degrees Celsius. So therefore here option A is correct. Let's take a look at the next question. This is also from the thermodynamics. So we are given a situation where a vessel has two compartments of volume V1 and V2. So let's draw it here and then try to understand. We are having a big vessel which is further divided into volume V1 and V2, volume V1 and V2, okay, containing ideal gas at pressure P1 and P2. So these two boxes contain ideal gases at pressure P1, and in another vessel it is pressure P2, and respective temperatures are T1 and T2, okay, respectively. If the wall separating the compartment is removed, so when this wall which separates these two compartments, when it is removed, the resulting equilibrium temperature will be. So let's say that when this wall is removed, then the resulting temperature of the entire system, that is equal to T. Okay, so because here we are having the same ideal gas here, and here also it's the same ideal gas, so that means we can assume that the heat capacity is same for the gas molecule in both compartments, so it's going to be common here. Okay, so now in compartment 1, you can say box 1, the total energy content associated with the gas molecule, that is let's call that as U1, and that is equal to the number of moles. Let's say we are having n1 number of mole here and n2 number of mole here. Okay, that is equal to n1, and then the heat capacity at constant volume n1 Cb, and then the corresponding temperature at which these gas molecules are there. Okay, similarly for the box 2, U2, that is equal to n2 Cb T2. Okay, now when here I have taken Cv as common because it's the same ideal gas in both compartment but at different temperature. So let me call the total internal energy of the system when the wall which separates these two systems, it's removed. Okay, so that is equal to the sum of the energy U1 plus U2, and that is equal to basically N Cv and the final temperature, where N is equal to N1 plus N2. Okay, so multiply by Cb into T, where T we are assuming to the final temperature. It is the final temperature. Okay, now the conservation of energy, if there is no heat loss to the surrounding, so then I can write this equation. So that is Ut is equal to U1 plus U2. So now we will substitute the value of U1 and U2 in this equation. This is equation 3. Okay, so from 1, 2 and 3, U, that is equal to N1 plus N2 into CBT, that is equal to U1, that is equal to N1 CB1, not CB1, it's CB T1 plus N2 CB T2. Okay, and we can cancel the common terms. Cv is the common term on both sides, so T becomes equal to T, that is equal to N1 T1 plus N2 T2 upon N1 plus N2, or this can be written as, now we will make use of the fact that for an ideal gas PV is equal to nRT moles. Okay, because it's an ideal gas, so definitely this is bound to satisfy this equation. So I can replace N1 equal to, so from here N will be equal to PV upon RT. Okay, so by doing that, so here we are left with N1, I'm going to replace it with P1 B1 upon R T1 multiplied by T1, okay, plus P2 B2 upon R T2 multiplied by T2 divided by, now come to the denominator. Okay, so in the denominator it is again same P1 V1 upon R T1 plus P2 B2 upon R T2. Okay, so we can cancel the common terms. T1 will cancel with T1, T2 with T2. Since we are having R both in the numerator as well as in the denominator, so this will also cancel. Okay, so ultimately we are left with the final result comes out to be equal to, this is equal to, okay, so the final temperature will be, after cutting the common terms, temperature of the system, the composite system, that will be equal to P1 B1 plus P2 V2 divided by P1 B1 upon T1 plus P2 V2 upon T2. So that's the final common temperature of the composite system. Okay, so let's take a look at which option matches with this result. Okay, so if you just take a look, so it is the option C, that's P1 B1 plus P2 B2 divided by this expression. Okay, so therefore C is the correct option here. So let's continue with the next problem. So here the statement is for temperature T1 larger than T2. So we are given that temperature T1 is larger than T2. Okay, T1 it's greater than T2. Okay, the qualitative temperature dependence of the probability distribution Fv of the speed v of a molecule in 3 dimensions is correctly represented by the following figure. Okay, so while it's the question basically from the Maxwell Boltzmann speed distribution, and while answering this question, the following two important points must be kept in your mind. The first point is that when temperature is changed, okay, the total curve area, which represents the total number of gas molecule in the system, total curve area does not change. That's the first point. Okay, because the curve area basically represents the total number of gas molecule, because here it's given one single gas molecule, I think, speed of a molecule in 3 dimension. Okay, but in principle, remember that the total curve area it gives us the total number of gas molecule in the system. Okay, it doesn't change when temperature is changed. So that means whether you are increasing the temperature or decreasing the temperature, the total curve area it's not going to be changed. Okay, and the another important point is, because curve area is equal to number of particles in the system. Okay, and the second important point is, at higher temperature, the distribution function Fv shifts to higher velocity. This is because when we are increasing the temperature of the system, certain gas molecule will acquire higher energy. So that's only feasible when this curve it will shift to the higher velocities. Okay, at high velocity. And another important point to note is that at higher temperature, curve become broader and maximum intensity is lowered. I will explain this point. is lowered. Okay, therefore if we just take a look at all the options, okay, the first point is that the total curve area doesn't change. So that means among these all of these two curves at temperature T1 and T2, the total area under these two curves, that should be equal. Okay, just by taking a look at the graph, sometimes it doesn't become clear exactly, but there is another hint here. At higher temperature, the FV curve, it shifts to the higher velocities. Okay, so that means here we are having T1, it's larger than T2, so that means the curve at temperature T1 should be at higher velocity, it should be shifted to the higher velocities. So therefore okay, so here we are having three such curves. Here the curve at temperature T1, it is shifted to the higher velocities. But now at the same time, let's take a look which curve satisfies another condition. The condition is that at higher temperature FV, it shifts to the higher velocity and curve become broader and maximum intensity is lowered. So that means in option A, the curve at temperature T1, which is larger than T2, T1 greater than T2, okay, it is shifting to the higher velocity region, and also the maximum intensity, it is lowered as compared to the temperature T2. That's the point. And also it is broadened with respect to the curve that is obtained at temperature T2. So therefore here option A is correct. Option A is correct here. So let's continue with the next problem. The statement is, a system of non-interacting spin-half charged particles are placed in an external magnetic field. So we are given spin-half particles, okay, which are placed in an external magnetic field at low temperature T. Okay, the leading behavior of the excess energy above the ground state energy depends on T, as where C is given a constant. Okay, so let's try to understand this problem. We are given a system of spin-half particles. So we are having spin-half particles. So that means in external field, let's say H. Okay, so when these spin-half particles they are placed in external field, so depending upon the their interaction with the field, either they can align along the field direction or they can align in a direction opposite to the field direction. So the spin possibilities are plus half and minus half. Okay, so here, so that means there are two possible energy levels basically. So when the interaction energy of a spin, okay, the interaction energy of spin with external field, that is equal to minus mu dot H. That's the interaction energy. Now when the spin aligns parallel to the field, when spin aligns parallel to field direction, so let me call that energy as as E1, which is equal to minus mu dot H. So when the spin is aligned along the field direction, so the corresponding angle between these two vectors will be 0, so it will be minus mu H, okay. And when spin aligns anti-parallel to the field, the corresponding energy, let's say it is E2, okay, and the angle between mu vector and H vector, that's going to be 180 degrees, so it will give us another negative sign because of cos 180, so the corresponding energy will be mu H. Okay, so and we call these we will label these as, so this is minus mu H and this is mu H, so therefore the ground state energy is minus mu H here. Okay, now since we have to find the excess energy above the ground state energy, so that means somehow we have to look for the expression for the average energy of this system, and that we can do by first taking a look at the partition function, and then from there we will find expression for the average energy of the system. And let's see how we will proceed. So the partition function for this system with two energy levels E1 and E2 is given by I'm writing for one single particle Q1, that is equal to gi exponential minus beta ei sum over I. Okay, so since these two levels they are non-degenerate, so g will be unity for both cases. Okay, so that means this is simply equal to exponential minus beta e1 plus exponential minus beta e2. Okay, so that means the partition function will be exponential e1 is equal to minus mu h, so minus will become plus, so exponential mu h by kt plus exponential minus mu h by kt. So that's the partition function. Okay, now from here one can quickly determine the average energy, which is given by E, that is equal to minus curly beta logarithmic of q1, and that is equal to minus curly beta of ln exponential mu h by kt. Please note that here k it's a Boltzmann constant. I am not putting the suffix b here, so but it's understood that it's a Boltzmann constant. Okay, plus exponential minus mu h by kt. Okay, so its differential turns out to be minus 1 upon exponential mu h by kt plus exponential minus mu h by kt, and then again differential of this quantity with respect to beta, which is 1 by kt. Okay, so note that beta here, this is equal to 1 by kt. Okay, so when we will take its differential, so we will have exponential term first, the first exponential term mu h upon kt, and then with respect to beta, so that is, it is basically beta mu h, so it will give us a term of mu h again while doing the differentiation. Now similarly this the differential of the second term exponential minus beta mu h, so this is, and the exponent is minus beta mu h, and its differential with respect to beta, that will give us exponential minus beta mu h and then multiply by minus mu h, so exponential minus mu h by kt and then multiply by minus mu h. Okay, now after adjusting the terms in the expression, so this is equal to, so I will take here mu h outside, so this is equal to minus mu h, and inside the bracket we will have exponential, this the terms in the numerator, exponential mu h upon kt minus exponential minus mu h upon kt divided by this and the denominator here. Okay, exponential mu h upon kt plus exponential minus mu h upon kt. Okay, so let's note this as, let me call this as equation 1, the expression for the partition function. This is our equation 1, and let's call this as equation 2. Now the excess energy from the ground level, the excess energy from the ground level is given by, let's denote that as delta U, and that is equal to the average energy minus the ground state energy, so that is E1. Okay, so that is average of E, which we just determined and wrote in equation 2, minus E1. E1 is how much? It's minus mu h, so that means E plus mu h basically. Okay, now substitute the value of E from equation 2 and let's see what we obtain. Okay, so therefore the excess energy delta U, which is equal to the average energy that we just obtained for the system minus of mu h, and that is equal to minus mu h and then exponential mu h by kt minus exponential minus mu h by kt divided by exponential mu h by kt plus exponential mu h by kt plus mu h. Okay, so we will take mu h outside and then try to solve it. Mu h, so from here we will obtain 1, so I am writing it here 1, and then here we will have a negative sign with this term 1 minus exponential mu h by kt minus exponential minus mu h by kt upon exponential mu h upon kt plus exponential mu h upon kt. Okay, so now I'm going to write here the direct expression, because this can be solved easily by taking the LCM. So in the LCM we will have this term, so after multiplying this term here and then adding this term, some of the terms will cancel, and finally after doing that mathematics here, so delta U, the excess energy term, comes out to be equal to mu h multiplied by 2 exponential minus mu h upon kt divided by exponential mu h upon kt plus exponential, so it should be minus here, exponential minus mu h upon kt. Okay, and this is in principle equal to mu h exponential minus mu h by kt divided by cos hyperbolic mu h by kt. So therefore at low temperature, what's the condition? Okay, therefore at low temperature, so the leading behavior of the excess energy above the ground state energy. Okay, so this is what we have obtained the expression for the excess energy above the ground state energy, and the leading behavior determined by the exponential function, and this one. Okay, so therefore the delta U, it is proportional to exponential minus mu h by kt, or you can say it's proportional to exponential minus c by t, where c is given by, where c is equal to mu h by kb, so which is a constant here, positive constant. So therefore the correct option is the c is the correct option here. Now let's take a look at the next problem. So we consider a system of two Ising spins S1 and S2, which can take value plus 1 and minus 1. Okay, so with interaction energy which is given by this expression E, that is equal to minus J S1 S2. So when it is in thermal equilibrium at temperature T, for large temperature, so that means for large temperature the average energy of the system varies as. Okay, so we can quickly evaluate the average energy of the system once the partition function is known to us. But in order to calculate the partition function, we must be able to understand what are the possible configuration or the microstates that exist for this particular system. So let's try to understand this problem. So we are given that the interaction energy among two Ising spins S1 and S2, that is governed by the expression E, that is equal to minus J S1 S2, where it's given that both S1 as well as S2, they can take a value of either plus 1 or minus 1. So that means when spin is aligned in the upper direction, we will take this as plus 1, and if it is aligned along the downward direction, then we will take this as minus 1. Okay, now let's try to work out the various configurations for these two spins and accompanying to this condition. Okay, so I'm going to draw a table here, S1 S2, and then the corresponding interaction energy E, that is equal to minus J multiplied by S1 S2. Okay, okay, so here the possibilities are when both of the spins they are aligned in the upward direction. That's the first possibility. So the corresponding interaction energy for this case is given by E1, that is equal to minus J. J is a constant here, also called as exchange integral in principle. Okay, so S1 S2, so S1 is here, it's because it's in the upward direction, so we will take plus 1 for the spin directed in the upward direction, and then multiply by plus 1 corresponding to S2 plus 1. Okay, so that is equal to how much? That is equal to minus J. Okay, similarly, when one of the spin is aligned in the upward direction and another one in the downward direction, the corresponding interaction energy E2 will be minus J. Okay, 1 multiplied by minus 1, because minus 1 for the spin aligned in the downward direction, so that will give us plus J. Okay, and for the other case, when it is in the downward direction, then the second spin in the upward direction, E3 will be minus J. Okay, for downward spin it's minus 1 multiplied by plus 1. Okay, again plus J here. Okay, now the third possibility, when both spins they are aligned in the downward direction and the corresponding energy is let me call this as E4, that is equal to minus J and minus 1 multiplied by minus 1, so this is equal to minus J again. Okay, so now if you just take a look at the possible accessible microstates, so we are having two microstates with same energy J. Okay, so here what I can do is I can call this a degeneracy of 2. Okay, similarly for the another case here, another extreme, it is minus J, the possibilities of minus J energy. Okay, there are two such situations. So again for this case also G is equal to 2. Okay, so therefore the respective partition function will be Q for this system, Q 2, because we are having two spins, so Q 2 TV, that is equal to Gi exponential minus beta EI, where I can take value from 1 to 2, because we are having only two energy states here. Okay, so and where the degeneracy of each energy level it's 2, so that is equal to 2 exponential. Now the first energy term, that is let's take the minus J first, 2 exponential minus beta into minus J, so that will give you 2 exponential beta J plus second 2 exponential minus beta J. Okay, so this is equal to 2 into exponential beta J plus exponential minus beta J. Okay, so now from here we can quickly determine the average energy. So average energy, that is equal to minus curly beta of ln Q2, and that is equal to minus curly beta of ln 2 into exponential beta J plus exponential minus beta J. Okay, and this is further equal to minus 1 upon 2 into exponential beta J plus exponential minus beta J, and then its differential with respect to beta, a factor of 2 will come outside, and inside we will have exponential beta J multiplied by J plus exponential minus beta J multiplied by minus J. Okay, so here after rearranging all the terms we obtain the average energy of the system, that is equal to, so after doing the rearrangements, minus 2J divided by 2, and then inside the bracket we have exponential beta J minus exponential minus beta J upon exponential beta J plus exponential minus beta J. Okay, now here in this expression we will apply the condition that when for large temperature for large T, the value of Jy Kt is going to be much smaller than unity. So under this approximation we are going to expand the exponential term by retaining only the first term in the expansion, or first two terms in the expansion, because the higher order terms, they are going to be even smaller than these two terms. Okay, so this is equal to minus j into 1 plus j upon kt minus 1 minus j upon kt upon 1 plus j upon kt plus 1 minus j upon kt, where k is a Boltzmann constant here. So this will cancel with this term, so 1 will cancel with 1, and ultimately we are left with minus j and then twice of j multiply by twice of j upon kbt divided by 2. Okay, so this is equal to minus j square by kbt. So or what is the statement? Okay, so it's given that the average energy, it varies at c by kt. Okay, so with c given by, so here we are having, so this is equal to c by kbt. So therefore c is equal to how much? This is equal to minus j square. So that is our answer. Okay, so let's take a look at the options. So therefore option B is correct here. So let's take a look at the next problem. It is basically connected to the calculation of the density of states. Okay, if the energy dispersion of a two-dimensional electron system is E is equal to U h cut k, where U is the velocity and k is the momentum, then the density of states dE depends on the energy as. Okay, so let's see how we can handle this problem. So we are given the dispersion relationship, which is E, that is equal to U h cut k. Let's call this as equation 1. Here U is the velocity and k is the momentum vector. Okay, so from here we can write the wave vector k as k is equal to E upon U h cut. Okay, so from here I can also write the expression for dk, because we need these quantities for the further evaluation of the density of states. So that's why I'm doing all these things. So dk, that is equal to dE upon U h cut. U, it's a constant, and h cut is also treated as a constant here. So let me call these two results as equation 2. Okay, now in two dimension, the allowed k states, this result you have to remember, the allowed k states from k to k plus dk. So that means we are talking about the density of states in the interval dk. Okay, are given by the expression dk that is equal to L square upon 2 pi k dk, or this is equal to ak upon 2 pi dk, where I have denoted a, that is equal to L square, that's area. Okay, so now let me call this equation as equation 3. Now in this equation 3 I will substitute the value of k and dk from equation 2, and then this result will be transformed in terms of energy, because we are asked the density of states in terms of energy. So now whether you write the expression in terms of wave vector or in terms of energy, the relevant density of states, they will not change. Okay, it's a merely transformation of the expression in terms of other variables which are connected with each other. So here wave vector k, it can always be written in terms of energy here by the simply it's an the multiplier that's going to be different. Okay, but the density of states, they will not change. So therefore what I can do is I can always write dk that is equal to dE, and that is equal to, now this expression a upon 2 pi and multiply by k. So k is equal to E upon U h cut. E upon U H cut and then multiply by dk. dk is equal to dE upon U H cut. Okay, so now this is equal to basically A upon 2 pi and then U H cut and its square multiply by E dE. So therefore we notice that the density of states dE it depends upon energy E, like this. dE it is proportional to E in 2 dimension. Okay, so therefore our correct option is C here. C is correct. Let's take a look at the next problem. Consider two different systems, each with 3 identical non-interacting particles. So we are having two systems where n is equal to 3, which are identical and non-interacting. Okay, both have single particle states. So it's really important to note this point. Single particle states mean so that means if we are talking about fermions, so no, we cannot accommodate more than one particle here. Okay, and the energies of these single particle states are labeled as E0, 3E0 and 5E0. Okay, where E0 is greater than 0. So this information is given to us. Okay, one system is populated by spin half fermions and another by boson. Okay, what is the value of EF minus EV, where EF and EV are the ground state energy of the fermionic and bosonic system respectively. So here what we will do is we will solve this problem in 2 steps. First we consider the particles to be identical fermions. So when we say that these are fermions, so that means they are subjected to the Pauli exclusion principle. Okay, which says that we cannot accommodate more than one particle in the same energy level with the all set of quantum number identical. Okay, but since it is given here that the because these are the single particle energy states. Okay, it's really single particle energy state. Okay, so that means at the max we can only accommodate one particle here if it is a fermionic system. Okay, so therefore the ground state energy for this 3 particle system is given by when we are putting one particle here, one here and the another one here. Okay, so and if we denote the energy of this system as EF, that is given by sum of these 3 different energies, that is 5 plus 3 plus E0, so it becomes 9 E0. So this is the ground state energy for fermionic system. Let's call this as equation 1. Now when we consider the same system, but now if we treat the particles to be bosonic. Okay, bosonic system or the so that means here the Bose-Einstein statistic will follow here. So again we will draw the same energy levels here with the energy value E0, 3E0 and 5E0. Okay, now boson can stay in a one single particle state also. Therefore the ground state for this particular system will be that all the 3 particles, they will be stick together in the one single energy state. So here for the bosonic system the corresponding energy will be 3 times E0. Okay, now we are asked what is EF minus EV. So EF minus EV, where EF and EV they are the corresponding ground state energy of the fermionic and bosonic system, and that will be 9 E0 minus 3E0, and that is equal to 6E0. Okay, so in my opinion this is the correct answer, but I have seen over the internet that a few people have done this problem in some another way, where they kept 2 particles in the ground state energy here, but the second particle they kept in with the opposite spin. But since it is mentioned that it's a single particle state, so then we cannot accommodate the second particle with the opposite spin here. So we can only accommodate one fermion here, so that the net energy of this system comes out to be equal to 9E0. So in my opinion here option A is the correct one.